Yo,
Oh, hey, Clinton. Hey, CJ. Good afternoon.
afternoon.
Good afternoon.
Good afternoon, y'all.
Are we gonna take notes today?
Yes,
Okay.
have those notes ready. Thank you. Everybody, good afternoon. Welcome to Pre-Calculus. It's our last class before we hit a nice week-long break next week. So yay. So, awesome. We're there, and it's great to have that because I know a lot of us are probably feeling burnt out. We've been already like months in with distance learning, and yes, it's been hard, but we're here. Well, welcome. So today's Thursday, November 19th. Tonight, we do have gratitude night. I'm just putting in the reminder there. It's from 6 to 7:30. We'd love you all to attend. Your teachers are like holding the event, and we're going to have activities for you. So just a little reminder on that. It's just an open invitation for you and your families. Um, and I'm also happy to send that. No, the title's actually coming up. LOL. Let's first do our attendance check question. Then I'll give you the title. The attendance question is, what's your favorite breakfast cereal? That doesn't mean necessarily that you have to eat breakfast. Just like a cereal brand. What's your favorite cereal brand? Or what's their favorite way to eat cereal? Then we'll check what you all have. Let's see. Mini wheats. Life. Oh, okay. I think is mini wheats healthy? I don't know. Life sounds healthy. Cheerios is healthy. Milk first, then cereal.
Mini wheat is, I don't know, it has a little sugar, but it's
Okay.
coated sugar. But the
I think
wheats
without
are healthy.
sugar, right? It'd probably be healthy on the top.
Yeah. But not all of them have sugar, only like half of them.
Okay. All right. What? Oh yeah, cinnamon toast crunch. That one's a good one. Waffles. Okay, that's a cereal. Okay. Hey, you could stick some waffles in cereal. Cocoa Pebbles. Cinnamon Toast Crunch is god tier cereal. Cocoa Puffs. You tripping? I don't eat breakfast. That's okay. I'm not a breakfast fan either, but I do like cereal. I sometimes eat it for lunch, or I eat it for dinner. I don't know. For me, cereals, you could eat it whenever as a snack. Um, Someone said, I don't mind what cereal, but it's always milk first, then cereal. What? Sorry. I do cereal, then milk. Soy milk.
I do it both ways. It depends on how much milk I got in the carton.
Nah, bruh, you never supposed to put the milk first. That's oh my
Bruh, if you only got a little bit of milk up in there, you pour the milk first and then you pour the
no,
cereal.
you put the cereal first and then you pour the milk.
Oh, because if you put too much cereal up in there, it's not gonna be enough milk.
Well, then why don't you think that
Like
there's
a
only a
you
little
problem.
milk, so you go put a little
Wow.
milk?
I had no idea this was actually a debatable thing. I should ask my advisory this question. So, I mean, the milk is already there when I get my second serving. I'll say that. Like, I don't slurp up the remaining
Yeah,
liquid.
no, I do that too. But like what I'm saying is like, say you still got like a whole box of cereal, right? But
Mm-hmm.
then your milk almost gone. Like you barely got any milk up in there. I
Mm-hmm.
pour the rest of the milk up in there to see how much I got. And then I pour the cereal because I know the milk gonna be gone. Whereas if I was to pour the cereal first, I wouldn't know how much cereal to put up in there because it's only a little bit of milk left.
I see. So that's the reasoning. Oh gosh, some of you have very strong opinions on this. Okay. For me, it doesn't matter either way, to be honest. But yeah. Okay. So let's see who else. Who else? What other cereals? What other cereal are delicious to eat? I don't know if mine's old school, but my family would always do. I know people probably hate this cereal, but cornflakes. But they would sprinkle like sugar on top with sliced bananas. That's how my family would eat the cereal usually. Banana.
Just unlocked the memory.
What was that?
You just unlocked the memory.
Yeah, that's the best. I remember those were the best. They would always sprinkle sugar with sliced bananas, and it was really good and really.
Wait, what did you say?
It was cornflakes, like regular old cornflakes.
Oh,
Sprinkle
no.
sugar, sliced bananas on top. Pretty good. All right, and then AJ says, "Have y'all tried root beer cinnamon toast crunch?" Yeah, that sounds. Well, I mean, I'm not gonna
That
yuck.
sounds disgusting.
I'm not gonna yuck.
It's alright. It's alright. It ain't nasty though.
I can't. Like, I could say my opinion, but it's okay. All right. Let me go ahead and see who we have here and who's absent. So I'm missing, according to the checkout, and who I like perhaps marked as they came on in. This is who I'm missing. So I'm missing Jalen, Tori, Denise, Brandon, Jyrell. Wait, do we got Ruben? Sorry, Ruben, are you here? Yes, you're here. Sorry about that. I'm missing Carlos, Kyla, Risha, and Celia. So that's who I'm missing. So let me know if y'all can help in reaching out and texting them. Otherwise, again, let me repeat. That's Jalen, Tori, Denise, Brandon, Jyrell, Carlos, Kyla, Risha, and Celia. So that's who we're missing here today. Thank you for those who are participating. Waffles. All right. I mean, waffles is good. All right, cool. Let me go ahead and enter this attendance. So yes, you want to make sure you have either notebook paper ready, or if you're the type who likes to do electronic notes, you can do that too. Either way, you're still taking notes. Just be ready for it. So here's our agenda, everybody. So we're going to talk about something called left Riemann sums. And we're going to be taking notes on it. We do have a Google form participation. And that's not going to be our checkout, though. Our checkout is going to be actually opening the assignment that's due today and getting started on it. So that's going to be our checkout. So basically, you don't leave after you complete the Google form. You want to stay for the checkout for your full credit for today. So asynchronous number 11 is due today. And you do have one more assignment before your break hits. So asynchronous number 12 is going to be posted soon. It's due on Sunday, and that's going to be your last thing. So it won't be too bad. I never give like more than 1 or 2 problems, unless it's like basic Khan Academy practice, but I never really give you that much per async. It's usually like a bite-sized kind of thing that's worthwhile to do. So just as a heads up on that. All right, so that's our agenda. Let's have our notes ready. Before we start our notes today, I'm going to quickly recap what we did yesterday. I think that was yesterday. So we were on Desmos and we tried to kind of figure out how to kind of estimate the area under a curvy rate graph using geometric shapes. Here's some samples of some of the work. I just took some screenshots. Look at the different ways that you all tried to figure out the area under this curvy rate graph. And yesterday's essential question was, I can investigate how to approximate the area under a function and interpret its meaning. So that was yesterday's. This is just recapping that. Also to recap, not only were we asked to first off try to figure out the area, but we were also asked to interpret what does it mean? Like what does the area under the curve actually mean? And as you can see right here, this, I just typed it up more neater. I took a screenshot, but the area under this curve represents total heartbeats for that 10 minutes that Bristol was doing yoga. So the total beats that her heart made in that time period. And how you figure that out is by using the big idea. You basically multiply the y-axis by the x-axis. So y-axis was your rate and your x-axis was minutes. The units that cancel out are the units of the x-axis, and you're left over with total beats. Again, that connects to our big idea, rate times time equals accumulated unit. That's what the area under this curvy rate graph represented. Yay, we got Jirel. Yay. All right, so just letting you process, you don't have to write this down. This was from yesterday. I'm just reviewing that fact on what we did and how we're gonna build into the stuff from yesterday into what we're learning today. So as you all saw, there's different ways you all can estimate the area under the curve. There's actually a formal way, and there's a way we're gonna learn. That's the thing we're gonna talk about today. This is where you wanna start our notes. This is what you wanna title today's notes. Estimating area under a function. And here's our learning target. I can explain how to approximate area under a function using Riemann sums. So this is the new thing we're learning. Riemann sums. And I'm going to talk about what in the world is a Riemann sum. But this is new. All right, take a few seconds to write down your title and learning target. Again, you always want to do this because you want to know what you're learning. You want to make sure that at the end of class, you think about, wait, did I reach that learning target or not? Do I need to go to office hours? It's just always good to be aware of your learning. And yes, it is 6th period. All right, let's have a few more seconds on this title and learning target. All right, I hope y'all got this down. And again, if you didn't, just go ahead and like on your own, you could go to Google Classroom and open up our slides. You're gonna find these notes in there, don't worry. All right, y'all, let's get started on this learning target. So what in the world is a Riemann? Again, you don't have to write this word for word, just basic main points. This is just an introduction, like what is a Riemann? So Riemann is basically the last name of a guy who used this approximation method to find areas under curves. If you want to look him up, his name is Bernhard Riemann, or Bernard Riemann. I think it's Bernard. Sounds more right. So that's the name of the guy. You can look him up. This is his approximation method. So Riemann used different kind of rectangles to approximate areas under curves. And we use his methods today to make precise calculations with the help of calculus. So as you can see right here in this picture, you don't have to copy this down. I included this in our big ideas packet once you guys take a look at it, but notice how he's approximating the area under this curve using rectangles. And notice as well that the more rectangles he drew under the curve, the better the approximation of the area under the curve was. So for this blue one right here, there's a lot of blank space, and this is not a very good estimation if you were to add up the areas of the blue rectangles. The red one is getting a little better. There's less space. There's a bit of overlap. Then the green one's even better, and as you can see, the yellow one is almost like a perfect estimate of the area under the curve. Not there yet, but it's pretty good. So using rectangles to approximate the area under the curve is the method that we're going to study. You all did different shapes, you know, in your Desmos activity the other day, but we're going to talk about this specific method of using rectangles, and this is called Riemann sums. Welcome for those who just came in. We're doing notes right now, so make sure you have your notes, note paper, and or if you're doing Google Doc notes, you could take notes like that by taking a screenshot and just typing out little additions to whatever I'm saying, whatever works for y'all. All right, let me also fix attendance. Thank you for those who are just coming in. Happy you're here. All right, let me leave a few more seconds on the slide. Again, you don't have to copy the picture or anything, just a general gist of like what is a Riemann. It's basically using rectangles to approximate areas under curves. And this is the method that we're gonna use, actually, Riemann sums. All right, let's move on, y'all. Again, you don't have to get word for word. This is just context. Like, where did this come from? Who is this? All of that. So we're gonna actually specifically start to learn about Riemann sums by talking specifically, and I already mentioned this, the more rectangles you draw, the better your approximation. But we're gonna talk specifically of something called, so there's different types of Riemann sums. This one that we're gonna look at is called a left endpoint rectangle type of Riemann sum. Now, what I'd like you to do is you could put this title. So this is a left endpoint rectangle. It's a type of Riemann sum. And I need you to also copy down the picture. I want you to be careful when you're making a sketch of this in your notes, or if you're taking a screenshot, it's even better because you don't have to be careful in your screenshot. It's literally the screenshot. But when you're copying this down, I want you to be careful because you want to be careful about the heights of these little rectangles. So this one meets up at 1, it's cool. This one though, be careful. It actually meets a little, the height of this rectangle is a little bit above 2. So be careful. This one is actually exactly at 4. And this one, I believe, is going to be a little bit above 6. So be careful when you want to be careful when you're scaling your graph here. And we're going to talk about what's going on in this graph in a second, but first I want you to copy it down and just be careful about the heights of those rectangles. Let me give you all a few to first copy this down and or take your screenshot. All right, I hope y'all had some time to do your sketch, take a screenshot, whatever it is that you're making your notes on. Let me go ahead and clear my little lines I made. Okay, so what do we need to know and what are we looking at? Okay, right here. So one way to estimate areas under a curvy graph is using this rectangle method that we call Riemann sums. So that's just the first bullet point. Next bullet point. In the visual right, we're using rectangles to estimate the area under the specific function is f of x equals x squared, and we're looking between x equals 1 and x equals 3. Sorry, we're getting someone. Yay, Brandon's here. So what does that mean? So basically, let me shade the area that we're interested in. So it starts at x equals 1. It ends at x equals 3 is what this is saying. So all the way up here. And basically, we're trying to use these rectangles to approximate the full total area under this curve. The full total area is the part I'm shading right here in blue highlight. I'm just gonna color this in. Now, of course, it's not a perfect approximation because you have some white space, right? Still left over. See? This white space right here, these like white triangles. So it's not a perfect estimate of the area under the curve. It is just a way to estimate though. It's not perfect. You can always like edit this to make something better. So this right here is f of the curve is f of x equals x squared. And for those who just came in, we're taking notes right now. We're learning about an approximation method called Riemann sums. Thank you for joining us. All right, so that's what we're doing right here. Next. In order to be precise, we need to have our rectangle heights in order to determine, in order to be precise, we sometimes need our function to be able to determine the heights of each of those rectangles, because we need the heights of those rectangles to find the area. Because remember, our goal is to find the area under the curve. The area under the curve is going to give us accumulation, the area under a rate curve, I mean. All right, another thing I want you to notice about this picture is that the base width of each rectangle is 0.5. So see how this starts at 1, then goes to 2? That means the width of each individual rectangle is going to be 0.5. The width of each one. So this one's 0.5. This one's also 0.5. The next one, they're all 0.5, the same width. Cool. That's going to make it easier for when we find the area. Because to find the area of a rectangle, all you got to do is base times height. Once we find the areas of those rectangles, we'll be able to determine an approximation of the area under the curve. Next off, let me have you think about, and let me erase the blue highlight right now. So I want you to think about why these are called left endpoint rectangles. You want to write this down. These are called left endpoint rectangles because notice how the upper left-hand corner of the rectangle is touching the graph. Let me circle those. See, this is the upper left-hand corner of the rectangle. It's touching our curve, it's touching our graph. So that's why these are called left endpoint rectangles. Super important because there's different types of rectangles. And these ones you want to know, they're called left endpoint. All right, let me leave this here for first off, any questions, or I'm also just gonna pause here so y'all can get this down, the bullet points. Let me pause for like 30 seconds. Again, the slides are on Google Classroom if you need to go back to them. But just in general, get these bullet points down and any annotations that are needed on this picture. All right, so those are the main kind of points. We have one more descriptional slide before we jump into the work of actually calculating the areas. But before we get started, here's some things that we need in order to calculate the area under a curvy rate graph. So how do we calculate Riemann sums? First thing, we need the rectangle widths. As you saw from before in our picture, we do have those. Each base width was 0.5. But for a different picture or something, you're gonna have to determine what are the rectangle widths. We also need the rectangle heights. And the rectangle heights are basically the y value on our graphs visually. So we'll need the y value. And in order to get the y value, we might need to use our function. Yes, I could slow for surely. I'll pause a bit before after each bullet. Hi, for those that just joined us, we're taking notes right now. Welcome, welcome. And we're learning of a new estimation method that we're going to talk about right now. Super important, something called Riemann sums. All right, so we just talked about how we need rectangle widths and we need the y values because those are the heights of the rectangles. We need to remember that we're going to add up all the rectangles because that's going to give us the total sum, the total area of our approximation. So we need to remember to add them up. That kind of relates to the sigma stuff, but we're not going to talk about that today, but just something to remember. We've got to add them up. Let me pause here. And I believe I have one more bullet. I feel like I have another one after this. And we need to remember the units, if any. So what I mean by that is remember when we were working with the heart rate, the Bristol's heart rate, we needed to know that on the y-axis was beats per minute, x-axis was minutes, because in order to determine what was the area we calculated, we had to multiply and then get that the rate represented, the area under the rate curve represented total beats. So we need to remember the units if we're given units. If we don't have units, then don't worry about it. So just remember the units if you have any. Because sometimes you're just asked to calculate without any units, like we're going to do in the next example. So we don't have to worry about units for the next one. No, I think there is one more bullet point here. All right. Yeah, I do have one. So subscript notation is one more thing we'll need to know to organize the endpoints for segments on the x-axis. So what I mean by subscript notation, they look like this. Maybe you've seen them before. It's like when you label something like x subscript 0 or like x subscript 1. Subscript notation is just a way to help organize and label things. We're going to be using it to label our endpoints in our diagram in a second. All right, let me leave this whole slide up for 30 seconds or so, and then we'll go on to actually calculating the area under the curve with that problem y'all drew. All right, I hope y'all got that down. Again, slides are on Google Classroom, just to go back on any bullets if you need to. Let's go on with the actual process though. Okay, so we're going back to the original picture you should have all drawn in your notes. So this was the one I asked you to already sketch. Remember, these are left endpoint rectangles because the upper left-hand corner of each rectangle is touching our graph. And we're using these rectangles to try to estimate the area under this curve. And this curve is f of x equals x squared. Now notice in this—
Should we draw that?
You already drew this from before in your
Oh.
notes. Yeah, so this is the same one. So we're doing this one. You should already have this in your notes. If you did not draw it, you want to make sure you draw it because we're about to calculate the area of the rectangles. Now I want you to notice that right here we don't have units. What I mean by units is the y-axis doesn't have a representation. It doesn't say beats per minute. It doesn't say miles per hour. There's no units in this problem. Therefore, we don't have to worry about units for now. We're just going to try to look through how to actually calculate the areas of these rectangles. All right, next thing that you do want to add to your picture is the subscript notation. Now this subscript notation just serves to help us keep track of which endpoint we're on. So x sub 0 corresponds to 1. X sub 1 corresponds to about 1.5. So this is 1.5 because the width of each base of the rectangle is 0.5. So this is 1.5 right here. 1.5. X sub 2 corresponds to 2. This right here is 2.5. And that's going to correspond to x sub 3. And then the last value, 3, corresponds to x sub 4. So that's why the subscript notation is there. It's just to organize your work. That's it. Other than that, we're not going to do much with it. All right. Now, let's proceed to try to calculate the area of each rectangle. First, notice how I kind of color-coded the first little baby rectangle in green. We're going to try to find the area of that green rectangle. We already have the base. We already have the base of the rectangle 0.5, but we now need the height. So what I'm doing up here, what I'm doing right here is the work to find the height of each rectangle. Now, for some of them, you don't actually need to, because for the first one, you already could see that the height was 1, right? But for some values, you're going to have to use your function to figure out the height. So what I did is I just took that first left endpoint value, I plug it into my function right here. It's right here, so 1 squared. 1 squared is 1 times 1, which is equal to 1. That means my first coordinate point is 1, 1. You can go ahead and label that. And that means that my area for that first green rectangle is 0.5. That's your base width, times your height, because that's how you find the area of a rectangle, base times height. And we got that the first area for that green rectangle is going to be 0.5. And I put units squared because usually area is squared because I don't have any units. You don't have to put this, to be honest, because there's no units. You could just put 0.5. That's okay. So let me just pause here to see if anyone has any questions on how I just found the area of this first green little rectangle.
No, but like, where do we put it? Like, there's we have like so much like notes and like we there's no space on bottom of it now.
Where do we put the? I'm sorry. Where do we put the areas?
The extra equations.
The extra equations. So basically right here, this is like scratch work that I'm doing on the side. So up to you where you put your scratch work. I would have at least your area calculations. Either you could put it to the side like how I'm doing, you could put it to the bottom, or you could put it on an extra sheet of paper on the side of it. Up to you, yeah. Oh, and then the reason for that is because I just want to show everybody where I'm getting all the stuff, all my information and stuff. Okay, thank you for your question though. Any other questions before I move on to the next rectangle? Try to find that area of the next rectangle. All right, let's move on to the next rectangle, everybody. Again, please make sure you're copying this down in your notes. Our Google form is going to be asking you questions about these notes. All right, All right, so let's move on to the next rectangle. I want you to notice that the next rectangle, the upper left-hand corner corresponds to the x value of 1.5. That means I'm going to take 1.5 and I'm going to plug it into my function to get the second rectangle height. So notice that's what I'm going to do next. That rectangle in red, I'm going to plug in 1.5 because that's where the upper left-hand corner corresponds to the value of 1.5. So that's the next value I'm plugging into my function. Let me just show you. So this function is getting plugged in by different values. See what's in the chat. What's the word under 0.5? Base. The word right here is base. Base times height. All right, so what I'm doing right here is finding the height of this red rectangle. And I did. I just put 1.5 squared. If you use a calculator, all you got to do is 1.5 times 1.5. You should get 2.25. So we have the base. The base is 0.5. The height is 2.25. We have everything we need to find the area of that red rectangle. So let's go to the side right here. This is my scratch. I'm going to do 0.5 times the height, 2.25, equals, and if you do the math, you use the calculator, I got 1.125 as the area of that red rectangle. Notice how it is more than the green one, which makes sense. Should be more. 1.125. That's that area. All right, let's see. Let me pause here. Does anyone have any questions about how I found the area of the red rectangle? You can notice what we're doing. All we're doing is base times height. But in order to find the height, we're using our function. Got to plug in the x value into our function to find the height. All right, y'all, we're halfway there. We got 2 more rectangles to do. And then we'll have a good, like an approximate estimate of the area under this curve between 1 and 3. It's not going to be perfect though, but all right, let's go. So I want you to notice that the upper left-hand corner of the next rectangle corresponds to the x value of 2. Therefore, the value that we're going to plug into our function next is going to be 2. I believe I color-coded this as purple though. Let's see. Nope, it's blue. I think the last one's purple. So this one is the blue one. And the height of the blue one is going to be if I plug in 2 into my function as shown here. So 2 squared, that's 2 times 2 gives me 4. So that's the height of the blue rectangle. And there's the coordinates if you're interested. So we have the base. The base is always 0.5 for this particular one. And the height is 4. So I'm going to multiply the 2 to get the area of the blue rectangle. And that's going to be represented right here. All right, I got 2. So 0.5 times 4 gives me 2. So that's 2. Again, it makes sense because the blue rectangle has more area than the red rectangle, and the red rectangle has more area than the green, so it's making sense so far. You should be getting larger. Got one more, but let me pause here to see if anyone has questions. One more rectangle. Okay, let's go on to the last rectangle, everybody. Almost there. Whew, okay. The last rectangle should be purple. Yes, it's color-coded in purple. I want you to notice that the upper left-hand corner corresponds to the x input of 2.5. So that means I gotta take 2.5 and I'm going to plug it into my function to find the height of this purple rectangle. So I'm gonna go down right here into my side work. I plug in 2.5 into my function, and the output, if you do the math, is 6.25. All right, so I got my height, I got my base, I got everything I need to find the area of the purple rectangle. And let's go ahead and see what we get. So 0.5 times 6.25, we get 3.125 as my area. And as a reminder, because I don't have units, I just put units squared. If I did have units, I would put what the units are, but so that's 3.125 right here. Again, notice how that makes sense. The purple area should have more area than the blue, red, and green rectangles. Ooh, so that was indeed a workout, y'all, calculating those areas. Imagine if we had more rectangles. Okay, so we calculated the area of each rectangle, but remember, in order to find a total approximation of the area under the curve, we have to remember to add up all these areas. So let's add all these up so we can get the total approximation. Adding them all up should give you 6.75 units squared as the area approximation. Y'all can double check that. But we went ahead and added up the areas of these rectangles to get 6.75. Double check that work. And let me know if there's errors, because I'm prone to always making little errors. It's just a fact. Okay, so we found the total area. We got a good estimate. Here's a question to ask. Oops, sorry. Here's a question I want to ask you all in the chat. So it's not typed out for me, but I'm going to go ahead and ask. Is this approximation, 6.75, an over or under approximation of the true area under the curve? What do y'all think? Is this an under or over approximation for the true area under the curve?
It's like an okay one, I think, because there's like a lot of space, right?
There's a lot of space, and by space, do you mean what do you mean by space?
The white?
The white, so like this right here?
Yeah.
And then there's this. Okay, so it's a good enough, but except for these white spaces, right, that aren't accounted for.
Mm-hmm.
Okay, and then it stopped at 3, so I think we have an additional one. I wonder if anyone has an idea how we would kind of get a better approximation.
Maybe you build another rectangle and then that would be it.
Build another rectangle and then that would be the extra area. That's an idea.
Yeah.
Okay, this right now is just open. We're gonna know how to get better at the approximations later on, but this right now is just an open question for everybody. So yeah, if we wanted the true area under this curve between 1 and 3, that's why I didn't highlight this part, because it's not part of it. We're just interested between 1 and 3. I would need to also calculate the area of these missing parts, which are coincidentally also triangles. So if we're able to find the area of almost triangles, they're not perfect triangles because it's still like curved. Like they're not perfect. Triangles could be used as an estimate as well, or we could also like add more rectangles or something. So that's just some things to think about. All right, y'all. I hope y'all got this down. And again, this is an approximation method, and we're gonna learn more about this after the break, after y'all have a break. But before y'all leave on that break, so actually, never mind, this is going to be our checkout, y'all. I thought we had time to at least have you all open up Async 11, but instead, Async 11 is due tonight, y'all. So again, my look for is that you at least open it. Look, I got Miss Clark here. She's a student. Anyway, so basically, like, whoever opened it, that's awesome. But I know it's due tonight. It's due tonight. So, but I mean, I could see who's opened it, and I see Gerardo has opened it. So that's awesome. But you want to open it, and your assignment is to make corrections to asynchronous number 12. And I also put, if you did not do asynchronous number 10, asynchronous number 10, no worries, because you could pick a sample response and revise that. What I mean by sample response is the one linked here when we did the similarities and differences activity. You can edit one of those, that's totally fine. But I think it's super important to improve and revise your answer. Even if you think you got it right the first time, I'm asking you to edit it by, if you feel proficient in your original response, I want you to revise it and add connections and justifications to the big ideas. And here are the big ideas. You want to kind of make connections to that. So if you scroll down, you're going to see this is the same assignment from asynchronous number 10, except one additional question is, what revisions did you make and why? So this is due tonight. I just want to make sure that y'all understand that, get to see it, get to open it, get to look at it. But yeah, so there's just that. And let's go ahead and jump into our exit ticket though, y'all. And it's going to be based on today's notes that we just took. Here's our exit ticket. And let me open it along with you. So in this exit ticket, it's going to ask you about today's notes. Number 1 says, in your own words, describe the process and purpose of calculating a left Riemann sum. So what's the process in your own words that we just did? Number 2, describe what the portion circled as part A represents. So I circled right here and I labeled that as A. In your own words, you're going to think about what it represents. Number 3, describe what the portion part B represents. What in the world is my side work right there doing? What's the purpose of it? And it's okay if you don't know. You could honestly say you don't know, just so I could get some feedback as to what I need to review when we come back from break. And then you're going to be asked about what does part C represent, and then part D right there at the bottom. And that will be, yeah, go ahead.
Can you email me it, please? Because I'm on phone and I don't want to do the thing on phone.
Perfect. Yeah, sure. And by the way, y'all, so when it's time to actually log out, I definitely want to see that your name shows up here. So don't just leave. So far, no one yet from this class has it done this. Let me email it. So it's Danny. You should receive an email for it. Awesome. So then basically once you're done and you submit, your name should pop up here. Once you do that, you're free to, enjoy your day, enjoy your break. And I hope I see you all at gratitude night, but don't leave until your name shows up, please, y'all. I want to make sure you get your credit.
Can you quickly go to what do we need to calculate remain sums, please? I just need to screenshot it. For the last part.
I'm sorry, what? This?
No, the what do we need to calculate remain sums?
The first
Riemann sum?
This right here, in your own words, describe.
No, like the actual like writing part, the copying part. I want to screenshot the part I missed real quick.
Which part is that? I mean, it's on our Google Classroom too, if you want to open that up.
Oh.
You could also do that, or it's, I don't know if you're talking about this slide.
Yeah, it's that one. Thanks.
Welcome. Did you get your screenshot?
Yeah.
Perfect. Yep. Also on Google Classroom if anyone's curious, but do take your time on this. Get your credit on this, y'all. Please remember to not log out until you've completed your form, please. All right, CJ's the first one done. Woohoo! All right, CJ, I'll see ya. Have a good day. All right, we got Ruben. Ruben's our second one finished. Ruben, I'll see ya. All right, we got Cyan and Gabriel. Y'all are free to go.
I'll see you guys later. Have a nice Thanksgiving break.
Yay. All right, thank you, Zion. I'll see ya. All right, we got a few more coming in. Gerardo, thank you so much. And Jasmine Montez, thank you. AJ, y'all are free to get going. Thank you so much for your work.
Bye, Mr. Dono.
Bye, AJ. Oh, sorry. Did someone else submit? My bad. All right, we got Sam, we got Yaisa, we have Sincere. Thank you, guys. I'll see y'all. Enjoy the break. We got a new submission here. All right, Rebecca, thank you so much for your thoughts, y'all. Oop, we got them coming in. Yay, Brenda, thank you so much. You enjoy your break if I don't see you later. Bye. All right, Miles, thank you so much. I'll see ya.
All right, bye. Merry Thanksgiving.
Yep, thank you. That's nice. I like that. Yay, Leon. Thank you so much.
Well, happy Thanksgiving.
Thank you. You too. Oh, sorry. Someone else submitted. My bad. Let's see. Oh, no, no one did. My bad. Oh, yay. Thank you, Rosario. Appreciate it. I'll see you. If I don't see you later, I hope you have a nice break.
I hope you have a nice break too.
All right. Bye. Oh, Danny, thank you so much. Can't wait to check out your.
Yeah. Well, bye.
Bye. You enjoy your break. If I don't see ya.
Well, happy early Thanksgiving.
Yep. Happy Thanksgiving. Thank you.
Be
Bye.
safe.
You too. Be safe.